Hi everybody, welcome to Physics. Tonight in this channel we will be making an interview to a very important person called Fernanda Flores Gomez, who made an experiment about our horizontal launch and will talk us about a little bit about it. So Fernanda, tell us, how's your experience been with all this kind of experiment, how you feel? Can you tell us a little bit about it? Thank you for this wonderful introduction. Well, yes, I've been working on this experiment where the objective was to investigate the effect of height in the range of an object in horizontal launch. Therefore, I had a series of results and graphs that I will show you on my next slide. But before beginning, I'll show you a video that explains everything that I'll be talking about.
In this presentation, we can see that horizontal launch occurs when an object is launched at an horizontal level and follows a trajectory moving in a parabolic path. This object is denominated projectile, which represents any body thrown by an impulse that keeps moving by virtue of its inertia and the acceleration of gravity. The velocity of horizontal launch is always constant, and therefore acceleration will be null, having the same values initial and final velocity. The mathematical model used for the purpose of this experiment is x equals initial velocity times the square root of 2 times height over gravity. The independent variable chosen is height, as I'll be changing it throughout the experiment. The dependent is range, that is affected by the change in the independent variable. And the control ones are mass, gravity, air resistance, object, and space, that will remain under control and therefore constant. The research question is, how does increasing height in horizontal launch affect the range of an object? And my hypothesis is, if I increase the height of an object with a constant velocity, then its range will increase as well.
Very interesting, right? Now I'll show you how I did the experiment and the results I got. Come on, let's go and see.
For my experiment, I used 3 wood sticks, a rubber band, a dice, scotch tape, a ruler, and my phone to take videos. First, 2 of the wood sticks were tied up to an iron railing for support using the tape with a separation of 8 centimeters. Marks were made to them with the measurements of the heights used for the experiment. As a guide to know the location of the rubber band, I used it as a slingshot.
Then I calculated the initial velocity for it to remain constant throughout the experiment with the formula initial velocity is equal to distance over time.
To achieve this, a third wood stick was tied up to the iron railing 9 centimeters apart from the other 2. The rubber band was tied up as well to recreate a slingshot, and by using a dice, it was pulled backwards 9 centimeters and then thrown away. See this in slow motion, you can see exactly where it fell, the time it took, and the distance covered. After obtaining this constant value, the dice was thrown with the recreated slingshot, but with a height of 20 centimeters. I recreated this experiment 3 more times and increased the height every 10 centimeters after throwing the dice by untying up the rubber band and attaching it to the mark with the next height. Quite interesting, isn't it?
To test my hypothesis, I recollected the data in this table and then represented it on this graph with 2 functions.
Inside the graph, we can see that the x-axis represents the height for being the independent variable and the y-axis the range, representing the dependent variable. The r-squared value is remarkably close to 1 and the displayed equation of y equals 1.55 x elevated to the power of 0.7 is different to the simplified theoretical model of x is equal to 1.23 of h elevated to the power of 1/2.
For the theoretical model, I combined 2 very important formulas, time and range, and we got this magnificent theoretical model. To get the simplified model for the hypothesis, the h was isolated and initial velocity times the square root of 2 times height became a constant value being 1.23, and we got the following equation.
After simplifying the theoretical model, I identified that the graph's relation is power type due to the root function, showing that the range will at first increase quickly, but then it will stabilize and look as a straight line. According to this model, we could realize future predictions. If the die was thrown from a 6-meter height, the range will be 3.11 meters. The correlation coefficient between the simplified theoretical model against the equation of Excel is remarkable, with a 79% difference. This happened due to the difficulties to maintain the initial velocity exactly constant at all times, as I don't count with a machine or special technology to achieve this. Other anomaly that contributed is air resistance.
In conclusion, we can say that the hypothesis that stated if I increase the height of an object with a constant velocity, then its range will increase as well, is correct. We can see that in the graph, the range is directly proportional to the height and it grows when the independent variable does. My findings match the experimental behavior, even though the theoretical model is different to the one in Excel. There's a slight difference, I must say. This happened due to the elastic potential energy of the rubber band that changed every time I untightened it and attached it again, as its capacity to stretch had a slight change. Also, the initial velocity wasn't always constant due to the technological difficulties. Wow, that sounds so interesting, right guys? Yes, and tell us, do you have any kind of recommendation for this kind of experiments? Yes, of course. Some recommendations I could give you for future experiments are to put the sticks in solid ground and attach them to an iron railing to not move and stay firm. Record every shot to know exactly the range it reached. Use something that is not big or heavy but not small either due to its rare resistance. That's why I use a dice. And put a stick to mark how much the rubber band will be stretched to keep the initial velocity. And that will be all my recommendations. A big applause for our companion. Great. Well, I want to thank you, Fernanda. Thank you much for coming with us. And I want to thank you for being here with us and listening to a child. See you later, guys. On the contrary, thank you very much for inviting me today to this show and for letting me explain you all my experience. See you later, guys.